what's the relation between antiderivative and the Riemann integral? The answer is there's no relation, which is counterintuitive because from calculus, or calculus 1, so we've learned that if little f is continuous everywhere over this closed interval, then we can have the following conclusions. Then if, let's say, the changing upper bound integral, fixed lower bound, changing upper bound integral, ft dt, for example, it's denoted as capital F of x, then we can show that capital F dash is equal to little f of x. And we can also have the following conclusion, that the Riemann integral of little f from a to b can be given by capital F of b minus capital F of a. So we have the following link between our Riemann integral and our antiderivative. We have such relation. But it's because we have this condition that f is continuous everywhere over this closed interval. Without condition, I don't know if the following conclusion is true anymore. Maybe it'll still be true under some loosened condition. Maybe under some generalized version of the fundamental theorem of calculus. Maybe it can still be true by loosening the condition a little bit. But this is, true under some certain conditions. Without those conditions, then there's no relation. Here's why. I'll give some example. First example. So I can give a function that has antiderivative but not Riemann integrable. So for example, if I have f of x is defined to be a piecewise function where when x is not 0, it is equal to x squared times sine of 1 over x squared. That is when x is not 0. It's also defined to be 0 when x is equal to 0, because here 1 over x is at the bottom, cannot be 0. So for this piecewise function, it's easy for us to find out its derivative. F dash of x is, so when x is not equal to 0, we can easily differentiate this expression. That is 2x times sine of 1 over x squared plus x squared times cosine of 1 over x squared. We have to use the chain rule we have to differentiate the inside function 1 over x squared. That is x to the power of negative 2. To differentiate that, we have to multiply by, first of all, negative 2, then x to the power of negative 3. Then we can simplify everything. So f dash is equal to 2x times sine of 1 over x squared minus 2 over x times cosine of 1 over x squared. This is when x is not equal to 0. We have the following derivative. If x is equal to 0, then f dash of 0 is equal to use the first principle. Limit as x approaches 0 of f of x minus f of 0 over x minus 0. That is the limit of what is f of x when x is not equal to 0. This expression, x squared sine 1 over x squared minus f of 0. F of 0 is 0 over x. Right, then we can simplify everything. F dash 0 is equal to limit as x approaches 0, x times sine 1 over x squared. That is easily 0, simply because sine of 1 over x squared is bounded. Then x approaches 0. The whole thing approaches 0. No problem. So just for this f dash of x, f dash of x, also as a function, actually has antiderivative. Derivative over the interval. For example, 0 to negative 1 to 1. Actually, it has antiderivative over the entire real number line. But of course, has antiderivative over this closed interval. So what's its antiderivative? Its antiderivative is given by little f, because the derivative of little f is given by f dash of x. When x is not equal to 0, given by this expression. When x is equal to 0, given by 0. So this is when x equal to 0. Right? So really has antiderivative everywhere. Then of course, over this closed interval, is it Riemann integrable? It is not Riemann integrable. Simply because the function f dash is unbounded nearby 0. Because when x approaches 0, 2 over x approaches positive infinity or negative infinity. Right? When x is very close to 0, this term is very, very large. It's unbounded in any deleted neighborhood at 0. Right? So because a minimum requirement, a necessary condition for a function to be Riemann integrable is that it has to be bounded over that interval, right? But over this closed interval, it is already unbounded. I haven't proven that theorem before, but in the future I will prove that a necessary minimum requirement for a function to be Riemann integrable is it has to be bounded in a future video. But I'm done with the first counterexample where a function has antiderivative, but it is not Riemann integrable. So now I'm going to give another example where the function is Riemann integrable, but does not have antiderivative. So here the function is given by f. Let's use g. Let's use g. So g of x is given by 0 when x is larger than or equal to negative 1, but smaller than 0. It's given by 1 when x is larger than or equal to 0 and smaller or equal to 1. So again, it's a piecewise function. Piecewise function. 0, 1, negative 1, 1. So when x is larger than or equal to negative 1 and smaller than 0, and we have a hollow point, or excluding 0, it's given by 0. So just this overlaps with the x-axis. Now, when x is 0 to 1, so it's given by 1. So this value. So here we have a solid point. Now, for this function, is it Riemann integrable? Obviously, yes. Right? Just the area under the curve. From negative 1 to 0, the area under the curve is easily 0. The area under the curve from 0 to 1 is easily 1. So, indeed, indeed Riemann integrable over the interval -1 to 1. In fact, first of all, the function is bounded. Then the collection, the set of discontinuous points, is a zero-measure set. So that's why it's Riemann integrable, right? So the only discontinuous point is at 0, which is a jumping discontinuous point. It jumps from left-hand side limit, that is 0, jumps all the way up to 1, which is the right-hand side limit. There is a sudden jump, leap. But even though it is Riemann integrable, it does not have antiderivative. Here's my claim. It does not have antiderivative. Right? So if we assume it has antiderivative, what contradiction can we have? Right? Suppose it has antiderivative, right? It should satisfy the intermediate value theorem, which I proved previously. So if a function is derivative function, meaning it has antiderivative, then over this closed interval, then it should take all the values in between fa and f of b. So closed interval ab is my -1 and 1. So supposedly it should take all the values in between g of -1 and g of 1. That is 0 and 1. So it should take all the values in between 0 and 1. How about just half? Right? Is there some constant c inside the open interval so that g of c is equal to half? No. Because the only values that the function takes is 0 and 1. Piecewise function, 0 and 1. There is no such an x value that makes the function value equal to half. Can never equal to half. Right? So therefore, already contradicts with the intermediate theorem value property, which means that function g does not have antiderivative. Right? We can also see that through the second part of the double theorem, which says a derivative function, any derivative function cannot have discontinuous points of type 1. So discontinuous points, jumping discontinuous point is also type 1. Right? So it cannot be a derivative function. You see, the problem that's causing this function to not have antiderivative is the point 0. That's the problematic point, because there is a sudden jump. In other words, this function g does have antiderivative over its subinterval. Subinterval, for example, subinterval of just from -1 to 0 excluding 0 and 0 to 1 excluding 0. Those subintervals, yes, it does have antiderivative. Right, but it just does not have antiderivative at point 0. That's the problematic point. But in summary, we still say that it does not have antiderivative over closed interval -1 to 1, simply because it does not have antiderivative at point 0. Therefore, we have this conclusion. So now the question we naturally raise is that, is there a function where where it is Riemann integrable, but does not have antiderivative over any subinterval. Not just at one point, but no antiderivative over any subinterval, no matter how small the subinterval is. No matter how small the subinterval is, in any subinterval does not have antiderivative. Is there such a function? At the same time, Riemann integral. The answer is yes. And I'll talk about that in a future video. And also, my previous example, first example where a function has antiderivative is given by this expression when x is not equal to 0, and given by 0 when x is equal to 0. Yes, does have antiderivative, but it is not Riemann integrable. Simply because the function has a problematic point at 0. Nearby 0, it is unbounded. So now the question that we naturally raise after that, is there a function that has antiderivative, but at the same time still bounded everywhere over some closed interval, but not Riemann integrable? Is there such a function? The answer is still yes. Still yes. So notice when I'm talking about not Riemann integrable, I'm talking about not properly Riemann integrable. So I'm not talking about improper Riemann integrable, because if it's improper Riemann integral, it's going to be, even though unbounded, but still may be convergent, the integral. But that's a totally different story. I'm talking about proper Riemann integral, which I will also prove in the future that if a function is Riemann integrable over some closed interval, then it has to be bounded everywhere over that closed interval. So all in all, in other words, the essence of antiderivative, or the essence of indefinite integral is in fact only differentiation. It is not integration. The essence of Riemann integral is integration. So there is an essential difference between antiderivative and Riemann integral. However, under some certain conditions, there is a linkage. There's a link between antiderivative and Riemann integral. But just in a vacuum, there is no relation at all. Right, so when we are doing antiderivative, when we are finding the indefinite integral, we're essentially performing the operation of differentiation. We're not performing integration. So it's essentially different from the Riemann integral.